Hello everyone, welcome to Concepts in Chemistry YouTube channel and also welcome to the Chemistry Concept Booster series. So in this video, we will be discussing a question from physical chemistry, particularly from colligative property uh, chapter. So this will be the 28th questions in Chemistry Concept Booster series. So let's start. So yeah, these questions I picked up these questions from uh, colligative property chapter, but yeah, this question seems somewhat different. But I hope and I also believe that after solving or discussing these questions, uh, you will learn a lot of concepts regarding colligative properties. So, and also by solving these questions, I think some amount of revisions also will be done. So let's read the question. So a dilute solution contain m moles a solute in 1000 gram of solvent with a boiling point elevation constant Kb. The solute dimerizes accordance with the reactions 2A, A2. K is the equilibrium constant for these reactions. The value of K, we have to find the value of K is. So I think we all know that there are four colligative properties regarding solutions chapter. So one is relative lowering of vapor pressure, second elevation of boiling point, third deflation of freezing point, and fourth one is osmotic pressure. So in these questions, it is talking about elevation of boiling point. That's why see in the options del TB is there. In the questions, no, there is no mention of del TB, only KB. So KB means boiling point elevation constant. So see in the options del TB is there. We all know del TB is the elevation of boiling point. That is T minus T0 means T is the boiling point of solutions and T0 is the boiling point of pure solvent. So let's discuss the answer. So before discussing the before going to the main point of the answer, so we have to uh, actually we have to know these things, at least these basic things. So from colligative property, we all know that Van Hoff I factor is there. So when it is used, Van Hoff I factor. So normally this is the colligative properties are. This is the relative lowering of vapor pressure. Del TB is the elevation of boiling point. Del TF is the depression of freezing point. Pi is osmotic pressure. So these four colligative properties has their unique expressions. So when we assume for a solute there is no association or dissociations, only we assume the solute as a particle, and we all know that these colligative properties depends on the number of particles or number of moles of solute. So if we assume that there are no associations or dissociations of solute, then we can write this del p by p0 equal to, it has some expressions, del tb equal to, we can write all know kb into m, del tf kf into m is molality, pi observed is equal to crt. So this is this upper term of this we can write like that. But when there is associations or dissociation of solute means we are considering A. See the questions. If we are considering A, here is 2 mole of A, but in the reactions it dimerizes. So actually, we are observing a dimer of this A solute. Means according to our calculations, there are 2 moles, or you can say 2 equivalent of A, but we observe the in result we observe a less value of colligative property. Means since colligative properties depends on the number of moles of particles or number of particles of solute, since in these reactions Actually, the solute dimerizes to form a dimer. This is 2 moles, now it's become 1 mole. So we will observe less value of colligative properties. In that case, we have to consider Van der Waals factor. So Van der Waals factor is defined as observed value of colligative properties, mean we are considering the actual value after dissociation or associations, observed value upon calculated value of the colligative properties. Means when there is no associations or dissociations, that is calculated value, and observed value is after association or dissociation. So I equal to observed value of colligative properties upon calculated value of the colligative properties. Calculated value means there is no association or dissociation. So now we can write I equal to del P by P0 observed. So this term is known as relative lowering of vapor pressure. Del TB is known as elevation of boiling point. Del TF depression of freezing point. Pi is known as osmotic pressure. So this whole term observed means observed value upon this calculated value. Del TB observed upon del TB calculated. So we can define Van der Waals factor like that. Now, so colligative property observes, any colligative property observes, we can write I into colligative property calculated. So if there is solute associations or dissociations, then we have to consider the I value, and like this colligative property observed equal to I into colligative property of calculated. And if there is no association or no dissociation, then I should be 1. The value of I should be 1. Means colligative properties observed equal to colligative properties calculated. So now see the solute, the reaction given like this: 2A dimerizes to A2. So see in the questions, so M moles are solute in 1000 gram of solvent. So we all know the definition of molality. Molality means M moles of solute in 1000 gram. That is called molality, or 1 gram, 1 molality. So definition of molality is if there is presence 1 gram of solute in 1000 gram of solvent, then that solution is called 1 molar solvent. This is 1 moles of solute in 1000 gram of solvent. 1 molar, not 1 molar. 1 molar is 1 mole of that is 1 mole of solvent in 1 liter. That is called molar, mole per liter. But molar solution is 1 gram of 1 gram. So so sorry, not 1 gram, that is 1 moles. 1 moles are solute in 1000 gram. If there is 1 mole of solvent in 1000 gram of solvent, then it is called 1 molar solvent, and 1 mole in 1 liter or 1000 centimeter, that is called molar. And if 1 mole of solute in 1000 gram, it is called 1 molar solvent, molality, and the previous one is molarity, 1 mole per liter. Or you can say 1 mole solute in 1 kg solvent. 1000 gram means 1 kg. That is equal to molality. We write as small m, molality. And in the case of molarity, that is capital M, molar solutions. It is 1 molar solution. So now, so 2A solute A, 2 moles of solute dimerizes to A2. Now, if when time t equal to 0, only A is present, this 2 mole A is present, there is no dimerization, means 0. At equilibrium, if alpha is degree of associations, now it's become m into 1 minus alpha. So m minus m alpha. Alpha is degree of associations, means from this m value, m minus m alpha. So we have to subtract the m alpha value, and m alpha upon 2 it's become. Since see in this association process, 2A become A2, means 2 mole solute A becomes 1 mole of A2. Then at equilibrium, the concentration or the molality of this A2 become m alpha by 2. means half of the previous means first the molality is m, degree of association is alpha. Now at equilibrium the concentration or molality of the solute A become m minus m alpha. M into 1 minus alpha means m minus m alpha. The m is the original concentration minus m into alpha. Alpha is degree of associations, and the concentration of A2 become m alpha by 2. Since is dimerizes, so it's become half of this m alpha value. So now from the equilibrium constant, yeah, on point. In case of dissociations, we write like if 2a, then it's become a plus b or a plus a. Then we have to write m alpha plus m alpha. If there is a plus b or a plus c, then we have to write each case m alpha means from 2 moles of a, it's forming 1 moles. So 1 moles of A plus 1 moles of B. Then we have to write M alpha, in this case M alpha and M alpha for each case. Now from 2 mole it's from 1 means it's become half. That's why we are dividing by 2, M alpha by 2. So from the equilibrium reactions, see, we can write K, that is equilibrium constant, equal to concentration of A2 upon concentration of A whole square. So in the equilibrium condition, the concentration of A2 means in terms of molality m alpha by 2, and the concentration of A m into 1 minus alpha, m into 1 minus alpha, the whole square. So, and for the given solutions, elevation of boiling point, we can write del Tb equal to I kbm. We all know the expression of del Tb, that is elevation of boiling point, equal to kb into m. For normal case, if there is associations or dissociations, we have to write I into kbm. So we saw there colligative properties observed equal to I into colligative property calculated. So this is kb into m. This one is calculated colligative property, means del Tb equal to kbm is calculated. But in observed case, since here dimerizations take place, means association take place, so we have to write the van der Waals factor. So this is observed equal to I into calculated. So I into kbm. Now for the dimerization process, we can write alpha, degree of associations equal to I minus 1, 1 upon 2 minus 1. So how these expressions comes? So to see, we have to consider a separate equations. So let's see the for associations and dissociations how these equations come. The degree of associations or degree of dissociations with respect to van der Waals factor. So how it's come. So let's see. So AXBY is a solute. Now it's dissociates into X mole of AY plus Y moles of BY plus. Now when T equal to 0, this C moles is present. If we consider C is a concentration, so in this case concentration means C mole per liter. So the whole solutions is 1 liter. So we can consider C as a mole. So C mole presents 0 mole 0 moles. So the whole solution is 1 kg means 1000 gram, and C are the mole number. So we can consider C as a concentration means molality, C mole per liter, or C is the mole number. Directly we can say C is the mole number. Means the whole solution is 1000 gram, and these are the concentration term means C mole per 1000 gram. So we can say C is the mole number of this. So initially C mole present, AX the solute, no dissociations initially means when time is equal to 0. Now at equilibrium conditions, for dissociation case, X mole of A, Y mole of B form. Now if alpha is the degree of dissociations, now at equilibrium, this AX BY solute concentration of that or mole number C into 1 minus alpha means C minus C alpha, and since x moles of A form and y mole of B form, then at equilibrium the mole number is x into C alpha, y into C alpha. So at equilibrium, total number of moles. So we have to consider first we consider that there is only C moles in actual or calculated case. But since dissociation take place, that's why we have to consider the all the particles, mole number of all the particles in the solutions. Ax, By, x, A y plus, y mole of Bx minus. We have to consider these three particles and their mole number. So at equilibrium, total number of moles of particles means C minus C alpha, x C alpha plus y C alpha. Now these are the total mole numbers. Initially it was C, only C. Now at observed case means actually in real case these are the mole numbers, total mole numbers. Now I value is observed number of moles of solute particle by calculated value of. So if we write I equal to observed number of moles of solute particle divided by calculated number of calculated value. So we can write I equal to observed value upon calculated value. Now observed value how much? Mole number C minus C alpha, this all term, and the calculated value means initially C, it's become only C. Now from these expressions, if we try to find the expression relation between alpha and I, we will find alpha equal to means degree of dissociation equal to I minus 1 x plus y minus 1. X and y are the mole number of cation and anion after dissociations. So x and y are the mole number of the cation or anion after dissociation. So see in this case, if alpha is equal to 0 means there is no dissociations, then alpha is equal to 0 means I become 1. This part becomes 0 means I become 1. So I become 1 means observed value is equal to calculated value. So when there is no association or dissociations, from these expressions we can say alpha is equal to 0 means no association, no dissociations, I equal to 1. This means observed value equal to calculated value. If alpha is equal to 1 means complete ionization. This solute completely ionized to form x mole of A plus, y mole of B plus. Now I become x plus y. So I become the number of summation of the number of cation or anion forms after dissociations. So in this case observed value equal to x plus y into calculated value. So since I become x plus y, now we have to put the value of I in this case. So x plus y into calculated value. This is for dissociations. Now see the association case. If n moles of A, n value may be 2, 3, 4. So n value of A, n moles of A after associations form n-mer, means either it is dimer, trimer, tetramer, pentamer. So this is n-mer. So initially the mole number is C mole, the n-mer is 0. Now at equilibrium condition after associations it becomes C into 1 minus alpha. Now C alpha by n. Since n number of moles, n moles of A or n number of A forming a single n-mer. This is if 2A forming a 1 mole of dimer, 3A forming a 1 mole of trimer. So that's why since that number of particles decreasing, that's why we dividing by n at concentration. So at equilibrium concentration, the mole number of the A and AN is this. Now I, the observed mole number divided by calculated mole number. So calculated mole number is C, same as previous C, and observed mole number is this C into 1 minus alpha plus C alpha by n. Now from these equations, if we want to write a relation between alpha and I, we have to find alpha. We obtain that alpha equal to I minus 1 by 1 upon n minus 1. So I minus 1 by 1 upon n minus 1. This is the relation between alpha in case of associations alpha and I. Now when alpha is equal to 0 means I equal to 1, there is no associations. When alpha equal to 1 means complete associations, I equal to 1 by n. So observed value of the in this case observed value equal to 1 by n into calculated value. For that case, x plus y means after dissociations, number of moles of cation and anion. In this case, after associations, what mar, which mar it is formed. N-mer means which mer. Dimer, tetramer, trimer, pentamer. That value is N means mar number. That is 2, 3, 4. 4 for tetramer, 2 for dimer. So from these calculations, we obtain alpha equal to I minus 1, 1 upon n minus 1. That's why in that case, for association, and in this case it is dimerization, that's why we write here I minus 1 upon 1 by 2. See, in this case 1 upon n. For dimerization process, n value will be 2. N value will be 2. So we are putting here 2, since it is dimerization process, and since it is association process, we are considering these equations, not the dissociation process. So 1 upon n, so we have to put n equal to 2 for dimerization process. So if we put 2, then we will find I equal to, from this expression, I equal to 2 minus alpha by 2. So this is the value of I. Now from 2 and 3, equation 2 and 3. So equation 2 means this is del T is equal to I into kbm, the observed value of elevation of boiling point, and 3 means the I equal to 2 minus 2 alpha. So if we put the value of I here, 2 minus 2 alpha by 2 I and kb into m. Now if we rearrange these equations, if we some rearrangement take place, means del Tb upon kb into m equal to 2 minus alpha by 2. So from these expressions, we can write 2 minus alpha equal to 2 into del Tb upon kbm. So alpha equal to 2 into 1 minus del Tb upon kb into m. So from these expressions, we now we obtain the expression of alpha, the value of alpha. So now from equation 1, see, in equation 1, the actual one, we have to find the value of k, where m alpha by 2 upon m into 1 minus alpha by 2 whole square. So there alpha is present in these equations, and see the options, there is no alpha value. So, and in this expression kb is there, m is there, so we should not change the value of m, we have to put the value of alpha in these expressions, then automatically we will get the expressions. So now see, the value of alpha is equal to 2 into 1 minus del Tb upon kb into m. So if we put the value of alpha in these expressions, now m by 2 alpha, we are putting 2 into 1 minus del Tb upon kb into m. Also in the denominator, m into 1 minus, this is the value of alpha whole square. Now this 2 cancel out, m into 1 minus del Tb upon km, this m square goes outside, and inside 1 minus 2 into 1 minus del Tb kb into m. So now we can write, so m, if we multiply this m inside the whole terms, means it's become m minus del Tb kb, this m, and after multiplication this m will cancel out. So m minus del Tb upon kb. If we multiply this m inside this inside the term, then it's become m minus del Tb kb. Now m square, if we did the calculation, so it's become kb into m minus 2 kb into m plus 2 del Tb upon kbm. So now in the numerator, m minus del Tb by kb, numerator denominator, so m square minus 2 kbm plus kbm means kbm minus uh, so m square m minus del TB upon KB upon m square. So 2 del TB minus kbm minus 2 kbm plus kbm means minus kbm whole square, and now this kb also become whole square, m become whole square because this whole term is inside the whole square term. Now this m square and this m square will cancel out. This kb square goes out, goes to the numerator, means to the this, yeah, this m square goes to numerator term as a multiplication form. So kb square into m, if we calculate this, m into kb minus del tb upon kb. So and in the numerator only 2 del tb minus kbm whole square. So now this kb and from this kb square 1 kb will cancel out. So we can write into kb into m minus del tb upon 2 del tb minus kb into m whole square. So this is the actual relations of the equilibrium constant of the diamerization process. So this is the whole calculations. So see kb into m, see the options, kb kb into m, yeah, the denominator term contain whole square term. So b c cancel out from a and b. In the denominator 2 del tb 2 del tb minus kb into m whole square. So 2 del tb minus kb into m whole square, 2 del t minus kb into m whole square. In the both case denominator are same. Now in the numerator see kb into m minus del tb, kb into m minus del tb. In this case 2 kb into m minus del tb. So option A is correct. So this these are the calculations in this. If there is any mistake, please you can correct yourself in your copy during writing these expressions. So these are just mathematical calculations, and in this case just some chemistry is there. So we have to consider the equilibrium constant like that, and we have to find the expression of alpha from this elevation of boiling point expressions, obviously considering the band of I factor. So for uh, association process, the value of alpha or expression of alpha equal to I minus 1 upon n minus 1. N, since it is dimerization process, so n should be 2. From this, we find the value of I is equal to 2 minus 2 alpha from these expressions, and this del t equal to IKBM. We found that alpha means degree of association equal to 2 into 1 minus del TB upon KB into M. Just we put this value of alpha in these expressions, automatically we will get the expression of k value. And these are the just I wanted to show the how to relate the degree of dissociation or degree of associations with phantom I factor. For dissociation, I minus 1 x plus y, this x plus y mean the number of cation and anion forms after dissociations, and the number of mer, that is dimer, trimer, tetramer, pentamer, is form after associations. In this case n is that mer number. So I hope you guys understood the whole questions and their regarding details explanations. So I hope from this question discussions, so you people, I hope at least learn something, some new concept by solving this new type of questions. So I hope this questions, this solving these questions will help you a lot for upcoming exam preparations. So you can easily solve this type of questions regarding uh, colligative property. So usually simple questions, they ask simple questions from colligative properties. So just to give you all some different concept, by solving these questions. That's why we set this type of questions. I hope uh, yes, I hope this, and I believe that this video or these questions will be very helpful for you. So that's all for today. Thank you guys. Stay safe, stay healthy. So bye.